All right, even though it didn't look like it, this is note card VC number 2, integration by parts. We don't have a Word document. All we have is a PDF, and you can't use Camtasia on a PDF. So for this one, I'm just handwriting until I have time to type them up. So you do have some extra information at the top of your note card about the steps to follow when integrating by parts. All right, so for our first example right here, once we establish that parts is necessary, you want to use LIPET, L-I-P-E-T, to help you determine what is the U part of this integration process. All right, well, following the LIPET guideline, L stands for logarithmic. We don't have a logarithmic factor. I is inverse trig. P is polynomial. X is certainly a polynomial, so we're going to start there. U is going to be our X. So in your space provided, just try and mimic this. So U is X. All right, we need du, which is dx. And we also need dv. Okay, just looking at the different components here. All right, well, if u is x, or x is u, then the remainder of the integrand, including the differential, has to be dv. Because we're trying to fit everything into either u or dv. All right, integration, u substitution, 1/2 e to the 2x. All right, the ultraviolet voodoo comes from this part right here, the answer part. Ultraviolet voodoo, hopefully to kind of help remind you how to do the setup. So I'm going to multiply here. Okay, minus the integral voodoo, so ultraviolet voodoo. All right, and we don't have a product anymore, so I'm going to pull the 1/2 out and integrate again. So when I pull the 1/2 out, I'm left with e to the 2x, which that antiderivative is the same thing here. All right, for example number 2, it is going to be integration by parts, going through the LIPET again. Okay, our p is going to be present first, so that's our polynomial. So u is x, find the derivative dx. So if this is u, then everything else has to be dv. Easy enough, the antiderivative is going to be tangent. The antiderivative is equal to the ultraviolet minus the voodoo. Voodoo there. Okay, so we have a little bit of a problem here to find this antiderivative. Okay, it's going to require u substitution unless you've just memorized the antiderivative for tangent is the natural log of cosine. That's just one more thing to have to memorize. I think it's going to be just as easy to rewrite tangent as sine over cosine and do a u substitution. Not integration by parts, just a u substitution, where u will be the denominator and du will be the negative sine x dx, which tells us to bring in a negative and pull out a negative. So to complete the integration, all of this will be du over u. So that's going to go back to the natural log of the absolute value of cosine. And then our constant of integration as well. All right, for example number 3, notice there's not really a product other than natural log with the differential here. But go ahead and use lipid as a guide. Well, L is logarithmic. Well, there you go. U is going to be the natural log. Easy enough. Du is 1 over x dx. So if this is our u, then this has to be our dv. How nice is that? Because those antiderivatives just result in v being x. The product minus the integral of v du. I believe there was a 1 there. So that would be x times 1 over x dx. Okay, kind of convenient because now the x's cancel and all I have to do is integrate dx back to x and we'll be done. I'll do a little cleanup first. This is the integral dx. Antiderivative here is x. Don't forget your constant of integration. All right, if we take a look at number 4 and then go back up to the guidelines, look at number 5. It says if u is a second degree polynomial or higher, which in problem number 4 we do have a second degree polynomial, the tabular method is going to be the best method just because you don't want to have to integrate repeatedly. Okay, so a reminder about the tabular method. We set up 3 columns. The first column will be labeled the sign. We're going to alternate between positive and negative. Whew. The second column is going to contain u, whatever we decide u is, and all its derivatives, u and u prime. And the third column is going to contain the dv part of our original problem and the antiderivatives. All right, so once you decide that you're going to do the tabular method because u is this polynomial here and it's 2 degrees or higher, okay, go ahead and begin with x squared, find its derivatives all the way down until you get to 0. Okay, then what we did is we always started with positive. It's good to always start off positive. Alternated signs. All right, and then since we've decided this is our u, this has to be our dv, we leave off the dx and we just use the sin x here. Find antiderivatives. Check by differentiating. If I were to differentiate cosine, I'm going to get negative sine, but I want it to be positive, so I have to adjust with the negative. The antiderivative for negative cosine is negative sine. Check by differentiating. Sine's derivative is positive cosine, so I need to make it negative. Integrate again. Okay, so what we do is we start with u and go to 0 and then build our other columns according to the alternating sign, positive, negative sign, or the continued antiderivatives. All right, so let's build our answer. There it goes. All right, so our answer is going to come from the signed diagonal products. The signed diagonal products. So signed diagonal products. Oh, it'll disappear. So positive, positive, negative. So our first term of our answer is going to be negative x squared cosine x. All right, the next term is going to be the negative times negative, which is positive, 2x sine x. All right, and the last term is going to be positive, positive, positive. So this product is 2 cosine x, and then don't forget your plus constant of integration, plus c. All right, I don't know that I'd waste my time doing this unless I had a second degree or higher, but it sure is handy when you do have a higher degree polynomial. All right, taking a look at the last one, it's kind of an interesting one. Okay, similar to problem number 3, there's not really a product going on here other than arctan with the differential. So let's lip it. No log. Oh, there's an inverse trig, so that has to be our u. Well, it has to be, because the only thing dx can be is dv. All right, so u is going to be arctan. All right, the derivative of arctan is going to be 1 over 1 plus x squared. Had this been a composite function, then I would find the derivative of x or whatever that is and put it in the numerator and then square that down here. All right, dv has got to be dx, which means v is x. Okay, u times v minus v du. Okay, and notice what happens in the process of multiplying these two together. We've just created an integrand where I can use u substitution. So think about the denominator being u. Oop. Oh goodness, little technical difficulties here. I think you see where this is going though. We're going to integrate this. We're going to let u be the denominator. I'm going to have to, I'll get 2x dx. Goodness, I'm going to have to bring in a 2 and pull out a 1/2. So this ends up being du over u. There, I think it finally caught up. Minus a 1/2 natural log absolute value of 1 plus x squared plus c. All right, so integration by parts.